I hope you're not too sleepy, even though the NURBS deadline is just 1 hour behind us. And this person here didn't invent sleeping pills, but he invented something you maybe used in your coffee while rushing for the deadline. He namely invented sweeteners, and the way he found them was not by ingenuity per se, but by going for lunch breaks. So he went for lunch. His lunch was for some reason sweet. He then licked his fingers. They were also sweet, and he went back to lab, licked there the reagents and the vessels in there. They were sweet too, and that's the way he found sweeteners. But I think we shouldn't just rely on those unsafe lab practices or luck to find materials, but there's still some truth to this that materials discovery and chemical discovery is quite complex. So in the group I had my PhD in, and the one of Behrens Smith, there was the case that two PhD students tried to run the same reaction, to reproduce the same reaction. They were next to each other, doing the same thing step by step. And at one point, one of the PhDs was like, "Stop it. You should now stop what you're doing. Cannot shake this reaction. You have to stir it." Because apparently stirring was the essential part of getting this reaction to work. And at least to me, this is the starting point for our research for using machine learning, because very often the things we do have some patterns in them. So the PhD students doing that could learn from this. They could improve over time if they stir or shake because they saw some patterns in doing this. And the hope is we can learn from those patterns and then generalize in the future. And those patterns are, however, so complex that we couldn't write down a program. And if you are in this realm where coding it up in a program is super hard, but you have hope to learn something in there, you are in the world of machine learning. And very long time ago, not very long time ago, but some time ago, people have been starting to do this using atomistic idealized structures as a starting point, saying they know where all the atoms are, at least in their model, and based on this, then tried with this idealized structure predict what's happening. And there has been great success in making this scalable and efficient, and to now enable really highly accurate simulations at long time scales using tools like the ML potentials and stuff like this, where you can really have now insights at high accuracy levels for very interesting large scale, long time scale phenomena. However, you still in some way have to input your structure in there, and this often is quite difficult because in reality, if you make a compound, if you run a reaction, you don't just get this one perfect structure, and you don't modify it atom by atom, but instead you modify the recipe, the process you then use to create the structure. And so, in a way, the recipe is way more actionable because a chemist or material scientists can actually change this, whereas they won't change this atom by atom. It rather, this, if you do a recipe, very often will be a mixture of different conformers, different structures, different defect states, and those will all have an impact on the performance in the end. And very often, performance is then in a real life catalyst or something driven by defects. And this then rather is a very useful guide for insight, but not always then directly linked to what we observe from a given recipe in practice. And what my group aims for is to find ways to connect a bit more of those two sides, to have a bit more of the actionable recipes and how they then interact with the process on the other side. And this is important. There's a paper from, again, the time where I was at Bernd Smith's group, where you look at MOFs for carbon capture and you look at different lenses at this. So here you have different perspectives and you then rank the different materials. You have a library of 1,000 MOFs here, and you then rank how good they are and you use different ways to rank them. And the first way to rank them here is look at how selective they are for CO2 based on simulations. And then the other one here highlighted in red is that you do some life cycle analysis where you look at the total CO2 balance, if this thing would actually in the end give you some carbon negative material or not. You see here the ranking completely flips. So if you then just switch from this MOSIM ranking to something else, what would have been the best material here on top might not be on the top 10 in another metric. So really see that you need to really move away in some cases from this idealized structure to have in the end a really powerful material in a real process or real device. And as I said, our goal is to learn this, and we do this by learning functions with machine learning models. And if you do this with ML models, models are super flexible. They can learn basically anything if you use recent classes of models like deep networks. And you can say that they have this hypothesis space of functions they could learn. And within this hypothesis space, there hopefully is the right function. So hopefully you can express the right function, but it's only one part in this big space. So we have to find ways to compress this. We can either be clever and constrain the space of functions we express with our model, which is the orange part, or we have some intuition to give preference to certain functions, which we have seen with this bluish thing here, or you just add more and more data to this mix, and this way constrain what we can learn with our models to hopefully at some point converge to the right function within this big space of possible functions the model could learn. And in the following, I want to show all those different ways of doing things. On the one hand, being clever by incorporating physics to constrain the space of functions we learn, or by having this so-called soft inductive bias with the preference over function with the blue um, landscape we have seen here, or by getting more data and this way constraining what we learn. And then, of course, we should assess in a way what our functions do, because in the end, if we teach what functions are, we teach our students they have a range and domain. This is for ML functions not that easy. And so we have been also spending a lot of time in my group to measure what functions actually learn and where they can be used and trusted and where perhaps less so. And this is the mission today. We try to get to the actionable. We try to learn patterns to see them, use them for predictions, and based on those, derive actions to really have an impact on the actionable parts of material science. And I believe that if we do this right, we can build almost a flywheel for doing this. And for this, we have the different parts in here. We will get data in here. We have seen that data is a crucial part of this thing. We, of course, will manage data to make use of this effectively, apply it in different use cases, measure, of course, how well we do in those use cases. And then if we have this, we can apply algorithms to guide what to measure next and how to interpret data. In this way, increase how efficient we are in getting data. And in this way, also drive the efficiency with how we improve this pipeline because we have more data, can build better models, better algorithms, and this way have this flywheel effect. To really see this, I want to start at the beginning, which is getting the data into this flywheel. And this is, of course, something that if you do machine learning is at the heart of everything. And basically, no one has enough of it. And if you are very pragmatic, as we often try to be in my team, you can look around what there is out there for data in different materials domains. So here we see a plot that we made for this paper here, where we looked at how often you find different entries for different material classes in different data sources. So here you have repositories like Zenodo or DataCite, and here you have papers for different classes of materials. And you see if you look at just the y-axis of the different plots, so you compare papers against repositories, you have an order of 100, of a factor of 100 times more papers for material classes out there than you have entries in repositories. So you really see that papers are a really powerful source for data. And you even see that just about talking about the slide, already 10 papers have been published out there. And if this is good or bad, we can of course argue, but it's a fact that we have a lot of stuff being published in papers, and also we as scientists learned from papers in the past, and we still do so. And this, of course, isn't a novel observation. People have been doing this over time, trying to see how they can leverage published data. This is an important paper in the field that I'm working in Helmholtz, which are solar cells, and there Eva Unger and Jesper teamed up to mine with a huge team of students, more than 40,000 solar cells. And with this, they read papers by hand. So they had people look at the papers, extract data by hand, and in this way build this data set by really a lot of manual grunt work and labor for doing so. And this then gave you kind of this plot here, where you have each point being a solar cell, and then look at over time here how over time the efficiency of the solar cells changes. And of course, you see that it increases over time, but you also see that at some point there is no blue dot anymore. And of course, this isn't because people stopped doing solar cell research. Of course, it's still very active, but because they just stopped adding papers to a database, because at some point the paper here was published and there was less of a reason to add data to this paper in here in this manual, very time-consuming way. And so the question we then ask ourselves is what the impact of this is. Because if you do this manual extraction work, which is super powerful and important, at some point you will stop. You won't do add any addition anymore to the data, but the field will still grow. You will still have new papers being published in the field. And in this way, the gap between what you have and what the field now knows starts to grow over time. So with this manual creation that you stop at some point, you will have this growing knowledge gap over time, which can be a big problem if your field explodes and learns a lot by publishing new papers. And so our goal here was that we try to kind of get rid of this problem by automating the extraction of data, by having a pipeline that just directly reads papers itself and adds papers to a database by just doing it automatically. We call this Perla, and you have here the links for it. And the workflow there is that we have a bot that reads papers from the journals. It has RSS feeds. It checks if it has access to them, if it's open access. Then it has some classifiers to check if they are perovskite papers and so on. It then goes into a queue for extraction, and then the LLM extraction pipeline will pick it up there. We have some tricks in there to make it work effectively, or some fallbacks if there are issues to then retry extraction. And after that, we have one of the most important steps in there where we try to check if the extractions make sense by having some consistency checks. So we check if the numbers internally make sense and if they have the correct links to each other, because often there should be a link between two fields. We can check for this, and in this way increase consistency of the data. And if all of this passed, so if we went from journals through the LLMs to then the checks, we can after that publish this in a repository, in our case, Nomad, with an API to make it useful for everyone in the world. And then you see very interesting things happening. So you see here how the band gap of the perovskites change over time. You see that we had before our update, so at this point here before 2022, the old database kind of stopped adding things. You had mostly those higher band gap perovskites, and it now then changed to lower band gap ones. This you also see if you look at the device stack. So you have typically multiple layers in a cell where you have the adsorber, the perovskite, and also some transport layers. Before our update, it looked like this, where you mostly have MAPI as the adsorber and then corresponding transport layers. After the update, it really flipped, where you have way more mixed devices and also different transport layers. So the field really transformed because they really learned a lot of new stuff, which then wasn't at all in the old database. And this is super important because If you then train models to kind of learn and to predict devices and their performance, this has an impact. This is shown in this plot here. They predict two different things, the band gap and the efficiency with the same number of data points, but we in one case use the old data and the other one a mixed set of the old and the new data. You will see you have now much lower errors if you use this mixed data set. And I think this shows you that kind of the acceleration of the field makes somehow it almost ironic that this then limits how much you can apply ML, because if you don't have this updating database, you will just be always outdated and not be informed by latest innovations in the field. So we need to have a way to update the data to train models on to take advantage of the fast growth of the field. And this, of course, then also gives you other benefits. The data you get from models often is a bit more consistent. So if you apply some cross checks, for instance, here we can check if the efficiency matches up with other things we extract. So this is known physics that should apply. And if we extract the efficiency and if we also extract those other numbers, we know that they should relate to each other in this given way. And we can check this for the old data here and also new data, and we see that we have much better consistency in the new data set in there. So this is very powerful, I believe, and thus we tried for different other cases from copolymer reactions to other kind of photovoltaics. And we also have teaching materials out there if you would like to learn more about how to do this correctly with different kinds of systems, be it agents or multimodal models. So this now has been getting us data from papers into a database. The question now is, what do we do with data to then drive our flywheel to help us design experiments or to analyze experiments? And one thing we often have to do there as scientists is to combine different kinds of evidence. So you might have different measurements, and very often one measurement doesn't give us a full picture. We often have to combine different measurements to really understand the full perspective because they all are just different lenses. So if you have the case that you are now a chemist, one thing you often do is you measure something in a lab. You then have a sample here in your vial, and you would like to know what is in there in the sample. And then you measure different things like NMR or like Raman or IR. You then try to combine those different measurements, then based on this, figure out what chemicals you have in your sample in here. Right now, this is super hard to do with models. So models work great if they have just one input and then can try to give you an answer based on this, but doing this combination in a very transparent way is currently quite hard with models. But at the heart of science, and thus Adrian and Luke went out to figure out how to solve this problem. And this is here one way that we think about this. So if you have just your compounds without any measurement, every compound you could imagine is equally likely. And if you now start measuring things, you now add measurements to this, you can then kind of rank certain compounds higher. They are more likely because they agree with the measurement. You can add more measurements and more, and in this way, almost bisect the space by having the different measurements overlap. In this way, rank the right compounds, hopefully in the end the highest. And this way you have the answer because it's the one that agrees with all different lenses of all different measurements that you made in the space. And so what we try to do is to see how we can mimic this with models. For this, we have been using what's called contrastive learning. So we try to do here something quite interesting that we take so-called fingerprints. So we map data into a space that's high dimensional. But there you have in the end a vector for each data point. And we do something that we try to make this vector the same. So here you have the vectors, the same if they represent the same concept, in this case, the same chemical. So if you have the same chemical in the space of spectra, be it 1H NMR or mass spec, and in the space of just molecules, in our case, a text form for molecules, we try to make then the vectors for those the same. So that's the spectrum vector and a text vector for the same compound would be overlapping. If, however, you have now the spectrum vector and the text vector for different compounds, we push them away to make them different. So in this way, we have the same kind of concept, the same chemical with different perspectives, and we train our models to make vectors align if we have them from the same concept and go away from each other if they are from different chemicals. And we do this here first based on simulations on datasets from IBM mostly. And then later we fine tune and do a lot of other tricks with augmentation to make it then also work on experiments. And here you see what then happens in practice. We can now do something super cool because we can query databases of molecules. You see here databases of molecules where each molecule has one vector, one fingerprint. Using spectra here on the right, we can then just compare the vectors for spectra with the ones for the compounds. And since we aligned them, if it's the same compound, they are aligned and close and have a low angle between them. If they're different, we push them away. We can now see what vectors are most similar in this way, retrieve molecules by putting spectra into a database. And this works quite well. You see here how often we have the right compound at the top of the list. So we rank the compounds and we look at here how often we have the right one at the top of the list. So rank 1 would be here the best, of course, or rank 0. And you see here, if we add more evidence on the right axis, we of course make the list, the range of the ranks smaller and more focused on top ranks. And we also have the right rank very often at the top of the list. But we have one problem still in there, and that is that chemists are creative. They like to make new things, and this, what I just showed you, only works in databases, so only on known compounds. If they make something new, and we won't find it in databases, so we have to also find a way to make something new in here. And Adrian, in this case, he made something quite clever. He also let the system evolve the compounds to see if he can now just evolve the molecules by adding, removing bonds or atom types to have better agreement of the, again, vector of those compounds with the ones of the spectra to see if we can push the molecule vector closer to the one of the spectra with just those generations here. And this again works quite nicely. You see here, if you look at how often we can elucidate based on spectra what the compound is, we can do so quite often. So you see we have in top one, so the first entry is very often the right one. And we also outperform what people have been doing before in other systems. But the most interesting thing is that we can also kind of look for mistakes in papers. So in this case, look at cases where people published compounds and were later proven wrong. So later was a revision of the compound where people then found that based on the measurements back then or some other things, they shouldn't have published this compound, but rather this one. And we did now something quite simple. We just threw this compound here with the corresponding measurements of the right molecule into then our system. We first of all found that those things are quite unlikely under our similarity function, would all give you kind of a red flag or warning sign if you deploy it for chemists. We can also evolve it and see that we very often, and here always, find the correct compound at the end of the evolution. It's, you see it's rank 0, much higher similarities, and we then always converge with the right compound here. So you really see how you can also find mistakes in this way. We can also played around with this and also tried to see how you perform against chemists. So here you have the case where we had 20 new raw spectra and we asked different chemists, be it NMR experts that have been doing this for decades, and PhD students to do just a task to go from spectrum to structure. And we also asked our model, and you find that we perform quite comparably to the humans. So you see, we kind of elucidate a similar amount of spectra in this quite challenging case of novel raw spectra. So this was, I think, one example where you can really see how you can use data effectively to drive decision making in a lab. We now also push this to robots to also drive their things more automatically to then have all this driving loop be implemented faster and faster. For this, we of course would like also to calibrate where we go, and this we do with measurements to really see what we do and if what we do makes sense to kind of stay on track and to also know how to best improve. We started this basically inspired by what we have seen in this paper here. This paper was something quite simple. We just took large language models and then fine-tuned them to be better at answering chemical questions, like predict if this phase of this composition will be cubic or if it will be just one phase multiphase if you make it. And questions like this. And for this, we just fine-tuned. That means we update the weights of the model to better predict those questions, and we then compare it against baselines. And this was quite good, surprisingly good. And we then wondered, why is this the case? Do the models know chemistry? So we tried to ask this to models. We spent a lot of time building good questions, diverse questions for different kinds of chemistry, different kinds of skills, and then asked both models. So you see models here on the y-axis and chemists here with the lines. Those questions, we had around 2,000 of them in the end in different skill levels. And we looked at how often models and chemists are right. So being right always would be a 1 on this axis, R on these questions. And you see that even now with those kind of outdated models, already humans were often outperformed by the best models. And of course, you could now start arguing if the questions are the optimal ones to ask, but in the end, they were novel ones, exam-like ones. We test our students in similar ways. So at least could tell you that we have to rethink how to test students, how to make exams work, but also how we deploy models in chemistry. Because if I would have now in my hallway a master student acing all the exams, the models here do, I would try to see how I can involve this person in my group in a way. But somehow those models are still a bit nuanced. So we saw that fine-tuning can be very interesting and performant. Here on the exam question, it works quite well. So we put it further, we pushed into the lab to see if they can be co-pilot, if they can be co-scientists. And there, in this case, you see here Mara with some collaboration partners in India went to the lab and we then asked different kinds of questions to our models to really see if they can assist us in the lab. In this case here, we asked, for instance, two kinds of questions. One question was like, tell me what you see. That means perception. Do you see a Schlenk line, a rotor web, something else? And the other one is way more reasoning focused. What do you believe is wrong in this image? Is there something that could blow up or explode, or is everything safe in here? In this case here, for instance, have the fume hood open, and this might be a safety risk sometimes. And these two kind of question groups are shown here in the lab questions. So you have here the equipment, which is the perception like, tell me what you see. And here you have the quality assurance, tell me what could blow up. And you see here that for the equipment, models perform okayish, but certainly much better than for the reasoning task about what could be unsafe in here. And I think this now comes to a point that mimics what we often also feel when we use the models, at least what I feel when I use the models. So they can be super impressive on certain tasks, like we saw with the exams, but also very flaky and surprisingly bad on others. And so we pushed further to understand what actually is going on there in detail, because we also found people publishing papers and how they use models to predict quite interesting, but also tricky to predict things like energetics of materials and solutions in the end of the Schrödinger equation. But you also have, of course, problems like even just counting well, which we also have a paper about if you wonder. So in this case, Nawaf teamed up with Santiago to look at just this question of like why we have the two things existing at the same time, that we have people reporting really powerful results by using LLM for predicting material properties, but we also cannot really count even with the models correctly. And for this, Nawaf looked for ways to convert materials, crystal structure into text, and then tried to learn from this text to predict properties based on text, to then see where it works, where it fails, and why it fails, to then see if we can explain why the two things are there, that people do amazing stuff, but we can still not count with those models. So Nawaf went out to explore all ways he could find to convert materials into text, be it by including local environments into a text, or by having symmetry in there, or other information types. And he built ways to really ablate if we show it or if we don't show it. So if we show bonds or if we don't show bonds. And then in this way, he built those very big tables and plots and spends tens of thousands of GPU hours to figure out what information helps models and what doesn't help the models. So here you see three different plots for three different properties to predict. We now have one kind of language model that we trained, and we then just show here how well, so in this case, lower is better, lower error is better, we perform for different ways of showing materials into text. So we have here a list of the atoms in a way, and then we have here kind of a smiles for crystals that has just atom types and bonds in there, or just compositions in here. And then we also color here kind of the type of information we have in there. So if we have geometry in there, or if we only have the atom types in there. And the surprising thing here is that if you add geometry to the mix here, so if you add now, look at those purple bars, they aren't much lower than if you just have bonding information in there. And this was in some way the first very striking effect to me, because I felt that if you provide the model more information, it should know more and perform better. But this wasn't the case here. So here we show more information. We give all the position of the atoms compared to just showing the bonds and the atom types. And we still do worse, which is very interesting, if not strange. So he said, perhaps we didn't spend enough money, so we have to burn a bit more money here to explore what's going on. And for this, Nawaf just scaled everything he could scale to just see if perhaps the model was too small or not trained well enough, and if he could just do scaling, bigger is better, and make it work in this way. So here we do two kinds of scaling. We do first data scaling, we train on more data, and we do model scaling, training bigger models. Again, we have different properties here. We have different ways of showing text. And in all cases, I mean, there is some movement, but it isn't super impressive. I mean, if we look at the range of the errors, of the error bars we have in here, the improvements are still within the error bars you can get. So even just throwing more and more data and compute at this doesn't really improve it in a really meaningful way here. So we said, this is super strange. At this point, we have to do something else. And of course, being this arrogant I felt I have to play God. So we played God in this case here, and we played God by inventing physics, by really tuning what the labels we train on, what the correct values depend on. If they depend on just the positions of the atoms, or all the composition of the atoms, and how important those different factors are. So if we have just the composition focus potential, or just the position focus potential, or something in between. Because this was something we were about. Why is now at some point this position not really helping the model? And is there some kind of threshold of importance in there? So we can this way now sweep how important position is compared to composition in our data. And we did this again for different kind of data sets to have different diversities of structures in there and different ways of showing materials in text form. So we start here with the SIF, of course, which you know with positions and atom types and symmetries, so everything in there. And we then also have stuff like just composition in there. And we also have baselines, in this case, SOAP gap plus fingerprint approach. And we now sweep through this alpha to have, on the one hand, just position focus, and on the other hand, just composition focus. So in this case here, alpha 1 would only have focus on what the atoms are, and here we would have no focus on what the atoms are, but only on where the atoms are. And you find here a very, very interesting gap between the models we have with the LLMs and the classical models, that we have a very bad performance if we have position focus, but they might outperform baselines if we have a composition focus in the potential. We then went deeper and found that this is probably linked because models behave a bit like n-grams, and then sampling positions and learning this is combinatorially complex. So just learning this is way harder with the inductive bias of LLMs. And we feel that this also explains perhaps what we see in leopards, where we have for certain properties, the gene N approaches here in blue outperform the LLM or text-based submissions by quite some margin. And then, of course, you can say, yeah, I mean, perhaps LLMs cannot do this for this kind of property, but you can still use tools. We can build so-called agents. And this has been very popular recently, where people give their LLM access to tools like a Python execution engine, a web search, a robot, or something else. And in this way, build agents where the LLM can take decisions in the world, use those tools, and then in this way, hopefully fix some of the gaps that the LLM has by not knowing how to do certain things, because it can then just fill those gaps by using the right tools. And that's the idea of agents. And we try to just see what the limits there are. We try to push what agents can do. And again, we teamed up with Anup Krishnan and Delhi and some other partners. And we built what we call Corral, which is a framework that is quite well built, I believe, for building agents and also for testing agents. And for this then for with this we then had this conclusion here you can find in this preprint, where we see that kind of agents perhaps don't perform as you'd like them to perform. And to just perhaps step back, what agents do, you see here that an agent will receive a request as a question. In this way, it will also have a bunch of tools, in this case, like add some solution, mix compounds, do some test, and it will then try to pick the right tool from its toolbox, call this tool, get an answer back, based on this, perform the next action with the next tool, again, get some response back. And in this way, try to call tools and do reasoning until it hopefully has the final answer for this question. So it will just go through this process of getting the question, the request, and then seeing if it can now use some tools productively, use those tools, and then with the tools, hopefully get you a meaningful answer in the end, or until you stop it. We did this process of building those environments with questions and tools you have just seen for quite diverse domains, from driving an AFM, a microscope, to doing simulations, to then doing more chemical things like planning reactions, or my favorite example of finding out what you have in your sample. And then we built those big plots here, and they're very busy, but I will go slowly through it. So we see here our different domains on the x-axis, and we group them here by what kind of skills they require. So in certain domains, so those here, you only have to run a workflow, and the agents basically only have to change the inputs for the workflow. But it's quite fixed. What it has to do is it only has to run certain tools in an almost predefined order, and there's no big reasoning or understanding involved about the problem space. If you have now reaction planning, you of course have to think about this combinatorially big space of what you could do to decompose your synthesis to have a good red synthesis in there. And if you do something like finding out what is in your sample, your life is very complex. You have to first figure out what your problem space even is. You have to kind of make hypotheses about the problem space, test those, and this way is divide and conquer to have ideally in the end some understanding what you're actually even doing in there. So here you have way more reasoning about the problem space being involved, and here you kind of just run a workflow. And then we have on the y-axis different approaches of building agents. We have on the one hand, as the main variants, the different kinds of models. So in this case, some frontier models from OpenAI and Anthropic. And then you also have what people call harness or scaffold, in this case, React and tool calling. And those are the systems that convert an LLM into an agent because they build the loop that enables the LLM to call tools or to then parse the outputs or to do this in a certain kind of order with reflection, with planning, or some other ways. And a lot of investment kind of goes into building better scaffolds. And then you, of course, have those being used with a model. And you can see here in coloring how well we do. So you see here for the workflow-driven applications, we do quite well. We have high scores. But if you then go to something where you have to reason more about the problem, you have much, much lower scores in here. So the coloring here is much lighter. The numbers are lower. So if you have to reason more about the problem space, those agents fail more often. The other very interesting fact is that if you look at the vertical axis, most of the color gradient is due to the variation in model and not due to variation of the scaffold. So the contrast between different models is way bigger than the contrast between the scaffolds. And it's important because it tells you that the biggest gain you can get is by improving the model. And the scaffold might help you a bit, but most of the variance of your performance is driven by the model, not by the scaffold around it. And you will still have very poor scores in those reasoning-heavy domains if your model is bad in there. We then did some deeper digging into what's going on in there. We tried to look at the ways the agents call tools and then classified in different kinds of process steps from making hypotheses, doing a test, having evidence. We then looked at how those things are linked. Because if you do science in a Popperian sense, you should in the end falsify your hypotheses, or you should in some way at least not throw away evidence you have seen while doing your experiments. So we kind of did this, that we looked through traces and kind of tried to see how the different steps are linked, if the treatment of evidence was careful, and if the model just made up stuff by itself or just tried to come to an outcome without going through this formal process of reasoning that in the end is very key to science. We have all of this philosophy of science with falsification, Popperian approaches to reasoning, and so on, which kind of give us this epistemic rigor we often assume for fundamental sciences in the end. Because if you go deep, knowledge is justified through belief. So justification and having some process insight is super important in here. So we have this process insight here in a novel way. We look at the different kinds of domains here grouped. So we have here the workflow driven domains, and then we have here the more ones we have to reason heavier to understand the space. And we then have on the x-axis different kinds of patterns of reasoning, and we kind of group them into ones that we think might be productive for science, like using evidence, and then we have some that we think are unproductive, like ignoring evidence. And you see that ignoration of evidence or kind of just doing judgment without support for its judgment is quite common in the end, happens in almost any trace. And this kind of tells you that those agents are kind of sloppy reasoners. And they might get you an outcome in the end, but the process they use to get there might not be super rigorous in the classical way we think about science. So if you have the standard of having this very high rigor in how you get to a solution, that you really use all the evidence in there, those agents don't do that. And they very often just do the opposite of this. They just put force to a solution in there. And for certain problem spaces, this will work well. So if you have a workflow-like problem space, brute forcing it might get you a solution in the end. But if you have to first understand your problem space, this will be quite expensive because you won't be able to really divide and conquer the problem space effectively if you don't treat evidence properly but ignore evidence as you get it. And I believe that this is now, I think, a very interesting playground we have, where we have many components in place, where we have different data sources. We built also novel ones to fix some of the agent problems. We are involved in Fermat to manage data effectively. We have applications. I showed you, for instance, the spectra applications in here. We have different sorts of tests for the models. I just showed you the ones we have for diving deep into chemistry or modeling of materials, but also now for modeling agents. And we also use it in different ways to kind of then drive decision making in the lab and beyond. And we feel that with this, we can build a flywheel, and we also try to involve people in there and help to onboard them, because we also have been involved with organizing workshops and conferences. And I believe that is in the end kind of will help us to kind of help the field evolve. Right now, we do this in a way with a great team of PhD students and postdocs, supported by funding from diverse funding sources. And hopefully, we also can do this together with all of you. Thank you.
Thank you, Kevin. Every time I listen to this, I learn something new. Yeah, good. Guys, do you have questions?
Can I ask a question?
Yeah, go ahead, Raymond.
So Kevin, really, really interesting and fascinating, I would say, work. I have a question regarding the database you mentioned about the perovskites. So you know that for the whole transport layer, because I have been talking to some experimentalists and they are interested in like maybe how to say design a new molecular for this whole transport layer. So in the database, is the structure somehow of the if it's a molecular, is it saved or easy, like can be readily fetched? I'm not sure, like
Yes,
maybe can.
I mean, this has been tremendous work by the Fermat team. So what they have been doing is they have like a full pipeline to, based on the chemical names we mined from papers, go to PubChem or other sources and then mine the smiles. So we have, I think, quite good coverage now to also have the smiles and the structure in the end of the different transport layers in there. And so if you would go to the database, to parallel, you can click on the different materials. And if we could then fetch the smiles, you can also see the molecule as a drawing in there. And what we try to do as a follow-up is to improve it because very often people report the same material compound in tons of different ways. They use different acronyms or abbreviations. And right now we have our kind of manually maintained mapping thing, but we of course also try to automate this to have a better synonym matching over time to further increase the coverage of for which compounds we have structures also in there.
Yeah, and also I maybe like for the solar cell, even with the same architecture, like different groups might report different PCEs, for example. Like, do you think if you want to use the data for machine learning, will that be a problem, or you
Yes.
will say, okay, maybe.
So, I mean, one thing that we did, but is hard to get right, is we, in contrast to the old data set, also did some work on mining the processing of this device. So in the old database, there was quite little detail on if they did spin coating and in what condition they did spin coating to make this device. We also have fields for this. And of course, the idea is that some of the variant is explained by people just doing different processing, a sinter longer, anneal longer, whatever. And this will cause effects. And the one I think interesting follow-up to do with this work is to increase further coverage of the processing data and then kind of learn what the impact of processing is, because very often you might have the same device stack, but it gives you different PCE because you have then cracks caused by different annealing or other things which are due to processing factors.
Yeah. And I have another question actually regarding the part you mentioned, this LM for which you also encode the material structure information. Because I just read one recent paper in this published by Nature Machine Intelligence, where in this they include, I think, also encode the material like crystal structure information using the mineable atomic cluster expansion, what Mace is using, and in their like a report on the metric, it seems that it kind of outperform other language model, but I don't think I don't know, maybe they didn't do like benchmark also compared to your model, but yeah, just one maybe comment. Like it seems that they in the result part they show that for example the formation energy or the convex hull, the prediction, the accuracy get quite enhanced a lot. Yeah.
Yeah, no, I think, I mean, this, what you describe, seems like a very reasonable way of doing this. I think what we have seen is that using LLMs directly, so kind of copy pasting your CIF file into just a text prompt, doesn't make too much sense. It's too combinatorially complex for LLMs to learn. But if you leverage the strength of a gene N or gene N-like architecture and couple this then with the flexibility and natural interface of an LLM, I think can build very cool things. And there have been different works that explore this, where they kind of project different kinds of graph-based models or other models into the space of an LLM. You can then start chatting to an MD simulation to ask like, where are the atoms and stuff like this. In the end, an idea would be like this. And I think this is way more interesting and powerful because they can leverage really that the gene N is built for correctly expressing geometries, and the LLM is optimally built to be flexible in expressing language, and modeling geometry in language is very combinatorially complex.
Yeah. Thank you. Thank you for the talk.
Yeah, but in this regard, a follow-up question from my side would be, so how do you think of combining such, expertise-driven descriptors with the language-driven descriptor, like say text? So then like to combine them as descriptors?
Hmm.
So then like like to do a bimodal machine learning.
Yeah, so I'm not sure if this is a published paper or if I saw it in peer review somewhere, but
Uh-huh.
what you can in principle do, and I mean, there are some simple ideas in this direction is that if you, for instance, have perovskites, you have some stuff that's very structured. So you have perhaps the graph of the molecules,
Mhm.
and some stuff that's quite flexible, like the text of the processing. And what you can, of course, think about doing is you can get the embedding for the structured parts, the molecules with a gene N or something, and then embed the text with an LLM, then concat this, and then pass this to another downstream model. And
Mhm.
this, of course, I think is a very interesting way forward because you can then leverage ideally the best of two worlds, where we can model some of the kind of structured way with the structured models and combine them with the fingerprints we can get from LLM embeddings for then the more flexible stuff.
Mhm.
And then, of course, you would need to figure out if you want to jointly train some parts of this and if you best how you best combine those embeddings. But I think it's a very fruitful direction to go into.
Yeah, good. I have two questions regarding the data extraction part. So then,
Mhm.
like, this question can be unfolded into two aspects as well. So then, like, Kapasi has this knowledge system. Like, I read the Reddit, the discussion there. It said that, this kind of knowledge management system is not applicable for a big volume of literature. So then,
Mhm.
like, what is your take on this point?
Yeah, I mean, this is some discussion we often have because especially if you build those data management systems and you want to get them used,
Mhm.
it's very hard to get them used. So I think there has been a push in different consortia or the NFTIs to give people very long forms to capture all the details in some kind of very big Excel file in the end almost. And this is not never used because it's
Mhm.
like too burdensome to use.
Mhm.
But would be in some way ideal for machine learning because everything is already structured and nice to fit into a model. Then have the other kind of extreme, which perhaps is a bit like the Capati thing you mentioned, where you just say throw something in somewhere and we then figure it out in
Mhm.
the end, which has a problem that you maybe still then lose some of the detail on the way. And my feeling, but I think we have no evidence of this, is that probably the reality or the best spot would be somewhere in between, where perhaps you try to enrich some of this unstructured stuff into a at least somewhat structured format to also get some feedback from the people who use it to enable them to query it more easily, to
Mhm.
perhaps spot already some mistakes in the extraction from them, and then have somewhat that lives between the two extremes. Because yeah, I think I agree that just having this big dump of everything in there will be tricky, or at least might come to problems in the end. But the other extreme we saw also doesn't work. We just force people to fill out those big forms. In the end, no one fills out those forms.
I see. But then on the other hand, if we try to digitize, all the literature, so then because we publish mostly only the positive results,
Yeah.
like then this could also be a kind of a hidden problem, right? So like if we are, trying to training the machine learning model and so on only on those positively collected data, so then we might also, not see the hidden, kind of challenges. So then how do you think we could solve this problem?
It's indeed a big problem, and I mean, we just submitted a paper to NERBS kind of discussing some of this. That I mean, you miss also all of the experiential knowledge. So, kind of, because if you act in a lab, you see color changes, you feel how things are. And this is never written down.
Mhm.
And I mean, one way is that, of course, let systems also in some way explore in the world. I mean, this is, I think, what you get if you let robots a bit explore chemistry materials themselves, that they can do experiments and then also learn from both success and failure, and then also get some of the other nuances that are never written down in a way. But it's again expensive and not easy to scale. The other thing is that we ideally would also get to a culture change a bit, because I mean some of this fact of not publishing the negative results is linked to what we currently perceive as a good paper or worth being published, and worth passing peer review or something. And I mean, in the end, it would certainly benefit the field to avoid wasting money two times to know some of the failures. And I think this requires kind of people changing bits like what they think about a publication, what it should be, and that it should not always be just positives, but also that negatives can be quite fruitful and perhaps often more fruitful than the positives.
Yeah, but I think both aspects you mentioned could then significantly change the research itself, right?
Yeah.
Like on the one hand, if we would then teach robots to do all the experiments, like to learn from scratch how then the knowledge system should be constructed, then like I'm questioning, like whether do we bother or should we then try to publish at all? On the other hand, like we human beings could then try to monitor the whole process and contribute. So then, like like the more I'm looking into the agent based systems, the more I'm concerned about. I'm just thinking, doesn't matter really to get another PRV paper or whatever. Like so then like it's waste of time. Honestly speaking, right? So then like, because this can be repeated maybe in 3 or 5 minutes by a robotic system if we could get really like such kind of for me doing calculations, like supercomputer working, I think this is easy to do. And then for the maybe those people doing experiments, if then all the labs would be automatized, then I think this is also only a matter of time to try with another composition and do all such kind of systematic measurements, right?
Yeah, I mean, I think there's a discussion that's perhaps best to have over some drinks, because it's a longer and deeper one. But I think in the end, what we somehow feel is that already right now, our system in science has some flaws or some things we believe are suboptimal, like being focused on certain metrics. It can be gamed quite easily. And I think now we just have ways to game those metrics much more easily, because we can just produce much more, much faster. And this then makes certain things we have now set in place make less sense, because if we can just publish papers as you want, counting number of papers doesn't make sense anymore at some point. And so, I mean, this perhaps the positive perspective in this, that we can have hope that perhaps some of the things we didn't like about how science is organized, or we felt were perhaps suboptimal, we have now a reason to change, because they will need to change.
Okay, good to know. Okay, another practical question from my side would be, like reading your paper, about benchmarking the knowledge of, like large language models and also chemists. So then, like, then you collect a lot of question and answer pairs. So then, like, do you think such kind of collection is still something worthy doing for another niche field, like, for us doing solid state chemistry or magnetic materials? So then, like, then do you think we still need to get such stuff, collected and then with the answers organized so that we can then try to test the performance of the large language model, or use such question answer pairs to reduce the hallucination?
Yeah, it's a very tricky question. So, because on the one hand, we would like, of course, that we have good knowledge of how systems perform. And for this, benchmarks are critical, and many things are currently not really measured properly, and having high quality measurements of what the limits are is essential to be able to improve them or to at least know where we can use them faithfully and where not. I think the problem we have right now is again one of the organization that many of the benchmarks are then also quite quickly being used to advertise new models or then overfit on them. So you no longer have this thing as this kind of neutral measurement device out there, but it's now part of this entire system where it's also in some labs being used to optimize models on or to advertise. And so having really neutral ways of testing models that also kind of adapt to overfitting is quite tricky. And I mean, there are some models being explored that you have some private data, especially if you don't develop models yourself, you might not kind of show what you test the models on, but you just keep it for yourself. If you are someone who can be trusted, this kind of can be a very good way, especially if you kind of have very challenging questions. So I think like all the just knowledge focused questions are almost too easy to treat because you can then just like memorize another textbook. But kind of deeper reasoning ones are hard to cheat, and especially if they're really novel ones. And the problem there again is that for most of the things that are super interesting, they, at least in research, often don't have an answer. So I have many questions about universe where I have no answer for,
Sure.
and I would like the answer for. But this, of course, is hard to benchmark because for benchmarks, you need to know what the answer is. And I think there's, again, an interesting regime where people push for building AI scientists to do research. And many of the things would like to use the things for, we don't even know what the answer would be. And it's very hard to test them unless you use them. And so many of the good evals you see right now are kind of very usage linked, that you just see what system in a controlled usage example gives the best benefits. But I think the underlying message is that evals would be useful in many cases, but it's very hard to build good ones.
I see. Good. Thanks a lot. So guys, any other questions meanwhile? I stopped the recording so that you can ask maybe your private questions.